I will now talk about the notion of closure of relations. Before I talk about the closure of relations, let me just say here that I am sure each and every one of you knows the notion of closure from a different context. For example, when we look at integers and summation, okay, so if you take two integers and sum them, you take the sum of two integers, we know that the answer is going to be, or the result is going to be an integer, right? So the sum of two integers is an integer. This is why we say integers are closed under addition. If you take two integers and subtract them, we will know that the result is an integer. Therefore, integers are closed under subtraction. If we take two integers and multiply them, the result, of course, is an integer. We know that integers are closed under multiplication. If you take two integers and divide them, the result might not be an integer. Therefore, we say integers are not closed under division. Okay? So when we talk about closure, we are talking about, if we talk about a set closed with respect or under a relation, we are talking about that the relation, all the elements in the set that we are talking about satisfy that relation. Okay, so let's look at this more formally. If we have a relation R on set A, and we have a property P of the relation, reflexivity, symmetry, anti-symmetry, transitivity, and so on. So we say that if there is a relation S with property P, okay, so there is a relation S that satisfies P, and this S contains R. Remember that relations are just sets, right? So if I have a relation S such that R is a subset of S, and R satisfies property P, and also the S is a subset of every relation with property P containing R, then S is called the closure of R with respect to P. Now, what does this mean, such that S is a subset of every relation with property P containing R? What this means is we are saying that S is a relation that contains relation R, but it's also the smallest such relation. S is the smallest relation that satisfies property P such that R is a subset of S. Okay? So if we have such a relation, we call this S. We call S the closure of R with respect to P. Okay? And let's actually get to concrete properties here. We start with the reflexive closure. If I give you a relation R on A, the reflexive closure of R is a set S that contains R, and S is also reflexive. Okay? So let's look at an example here. Let's consider the set A to be A, B, C. And let's consider R to be AA, BB, and AB. Okay? Let's consider this R1 here. R1, of course, is not reflexive, right? Because CC is not there. So what is S1 that is the reflexive closure of this? Well, R1 already had AA and BB. We need to make it reflexive, therefore we add CC to it. Of course, we have to have all the original elements that were in R1. So AB has to be there. So S1 is the reflexive closure of R1. But if we take R2 to be AA, BB, CC, and AC, let's say, and CB, what is the reflexive closure of this? Reflexive closure of this is the relation itself. R2 is already reflexive, so there is nothing more to add to it to make it reflexive. So S2 is really just R2. Okay? So the reflexive closure of a relation, you can first look at the relation itself. Is it reflexive? If it's reflexive, then its closure is the relation itself. If it's not reflexive, add to it the minimum number of elements to make it reflexive. Okay? Symmetric closure, if I give you a relation and that relation is symmetric, then you are done. Okay? If that relation is not symmetric, you need to add elements to it to make it symmetric. So if R let's say, is AB, BA, CA, AC, then its symmetric closure is the relation itself, because this relation is already symmetric. Okay? If R is AB and AC, this relation is not symmetric. To make it symmetric, we have to add to it BA, and we have AC here. To make it symmetric, we need to add CA. So this is the symmetric closure of this relation. Okay, so you add the smallest number of elements to it to make it symmetric. The last one is the transitive closure. It's slightly different than the reflexive and symmetric closure here, because we keep applying it repeatedly until we cannot add any more elements to it. So here we define R to the first to be the relation itself, R to the second as the relation composed with itself, R to the third as the relation composed to R to the second, and so on. The transitive closure is the union of R to the I from 1 to infinity. So think about transitive closure in terms of friendship. So when I talk about R to the first, it's the friendship, the direct friendship. So if A is friend with B and B is friend with C, then R to the 1 tells me that A is friend with B and B is friend with C. R to the second now tells me that the friend of your friend is also your friend. So R to the second says that if A is friend with B, B is friend with C, then A is friend with C. R to the third, the friend of your friend's friend is also your friend. So we keep applying it until we cannot add any more elements to it. So if I take R to be AB and BC and let's say CD, then R star is AB. Of course, we have to have the same elements from R in to begin with. And then let's start applying transitivity. We have AB and BC, therefore AC should be here. We have BC and CD, therefore BD should be here. Okay? Now we have AB and BD here. We have to add AD as well. Right? So we have AB, we have BC, we have CD, we have AC, we have BD, and now we have AD. If you look at it from, if you try to draw it, so if this is A, this is B, this is C, this is D, we know A is friend with B, B is friend with C, C is friend with D. This tells me that also A is friend with C. It tells me also that B is friend with D as well. But as well, it tells me that A is a friend with D because A is a friend with B, B is a friend with C, C is a friend with D. Therefore, we have A is a friend with D as well. Right? So this is the transitive closure of this relation. Okay? So you keep just applying transitivity to this until you cannot add any more elements. I mean, I can keep trying, but I don't see any other elements I can. For example, DA should not be in the DA should not be in the transitive closure because there's no reason to add it there. Okay? So this is what the transitive closure is.